Now, like so many other processes, we saw that this method is also capable of finding out the molecular mass of the solute. Now, what advantages does this have over the earlier discussed methods? Okay, see, one of the methods was elevation in the boiling point. So you have to take it to the boiling point. Fine. Before you realize how much is the elevation, and then from there you'll calculate the molecular mass, right? Similarly, for depression in freezing point, you will have to bring it all the way to the freezing point, right? Now what happens, certain molecules like proteins, okay, they get destroyed if you take it to the boiling point or bring it to the freezing point. Fine, they cannot withstand those extremes of temperature. So what happens, in such molecules we'd like them to be at the room temperature. Okay, we'd like them to be at the room temperature, and the advantage of the osmotic pressure method is that it is able to calculate the osmotic pressure at the room temperature. Fine. So the advantages of the osmotic pressure method. Advantages of the osmotic pressure method of finding the molecular mass okay. The first is that it is used to find out the molecular mass, molecular masses of proteins, polymers, and other macromolecules. They are macromolecules because their atomic masses are in the range of of 10,000 U and above. Okay. Fine. The advantage here is that the osmotic pressure measurement is done at room temperature. Okay. Proteins and other macromolecules get destroyed at the boiling or the freezing point. Also, it may so happen that their chains break. You see the trouble, the chains break. So instead of one molecule, you get 4, and you never know how many you will get. So those are some other chaos that creeps in when you start boiling it. Okay, so this method, which is being done at the room temperature, becomes more advantageous. It measures it in the original form. Okay, and the third one, which I do not think is a great advantage, and the third advantage is that the third advantage is that it uses molarity instead of molality.
But what we studied in the study of the chapter is that molarity is a more trustable figure.
When you are not a more trustworthy, when you are preparing the solution, then molality is very easily known, right? You have sugar, you have a kg of water, when you have prepared the solution. Once the solution is prepared, then calculating molality becomes difficult. You understand? When you have the solvent and solute with you, then calculating molality becomes simpler. Correct? But if there is a solution, calculating the molarity becomes and hence the calculation is easier. Molarity is independent of temperature. Molality. And how about molality? No. Why not? No.
Because it is molarity.
There will be slight change in density. There will be slight change in density, but then that is here also. That will affect the molarity as well. What will happen? You heat it, it will slightly expand, very slight expansion. But then both are getting affected in the same manner, right? Both will get affected. Here you have the number of moles remain the same, so it is only the volume expansion that will bother any of them, right? But it will, you see, it will affect molality less. The temperature changes will affect the molality less. Why? Because there it is mass. Mass will not change with temperature, right? This will change. Molarity will change. Okay. You were saying molarity or molality? Molality will not change with temperature. Correct? Here it will change. Molarity will change. But it will be very, very small. It is not a gas that will expand to some great volume, right? Suddenly. The volume change is very small. And that drop in density, that is so it's not going to affect you. But in a lab kind of process, actually, for knowing the albumin, the protein in urine, okay, you use these methods. You'll see there is albumin or maybe protein in your blood, or there you cannot subject blood to its boiling point, right? It will destroy. It will actually kind of change the whole composition. And you have taken a sample and you have got limited amount of blood, right? So you have to manage it with that. So molality is temperature independent, right? And the other thing which is very vital, which is more vital, that its value is high even for dilute solutions. is high even for dilute solutions, and hence the probability of error becomes lesser, right? For dilute solution, and hence probability of error is less. Okay?
Why are we writing even for dilute solutions? When we are talking only for dilute solution.
Okay.
Why are we writing even for dilute solutions when we have got this expression?
Even for highly dilute solutions. Okay, so okay. Polymers, if you try to dissolve polymers have poor solubility. Poor solubility in water. So what happens if you try to measure the elevation in the boiling point? We have been talking about the solutions, right? They are homogeneous. But what with polymers, where polymers have poor solubility in water and hence do not form a homogeneous mixture. Okay. But even if the solubility is poor, the osmotic pressure does not get affected, right? It still remains the same. So it is due to these advantages that we prefer the osmotic pressure method more than the other methods that we have studied till now, right? Which are theoretically possible, but for this kind of scenario it is not.